Hi, good morning everybody. Welcome to the class of the series of lectures on rate processes. Today I am going to talk on ultrafast processes. I will just give you brief introduction of this topic. Now, that is ultrafast processes in chemistry. Now, in our last lecture, last two lectures, we have talked about this electrode reactions, that is redox reaction which is going on at the electrode surface. That is when a metal piece is dipped into a solution containing electrolytes, then various things happen, and if you pass electricity, then various reactions may take place depending on the voltage, then current density, etc., etc. So, under that heading, one aspect which we have not talked about, if time permits later on maybe we can take up, that is corrosion. Maybe we will have a very brief introduction on that also. Now, we have talked about fast reactions, and now various methodologies may be adopted to detect the rate for those fast reactions, like stopped flow, then plug flow, then relaxation methods. So, these are used to prove fast kinetics. Now, yet another time domain is there which is faster than these fast reactions, which occurs maybe in less than a nanosecond, that is maybe in the picosecond time scale, that is 10 to the power minus 12 second, or maybe in the femtosecond time scale, that is 10 to the power minus 15. Imagine 10 to the power minus 15 second, and our persistence of vision is 1/10 of a second. So, how fast, imagine how fast those processes are taking place in molecular systems. Okay. So, that we are we are just going to talk about, not in great detail, but we will just give you brief introduction, because of the limitation of the scope, we may not be able to go deeper into the subject. Okay. So, let us look at the time scale of various processes and reactions related to chemistry. You see, it starts from 10 to the power minus 54 to 10 to the power 17, that is the age of the universe, and 10 to the power minus 54, that is the Planck time. You see, in between it is it starts from 10 to the power minus 15, minus 14, 13, 12, 11, and up to 10 to the power minus 3, or maybe even longer, that is second, 10 to the power 0. So, just look at the various processes. There are various processes, and depending on their time scale of observation, we can classify. First, let us have a look at let us start from the slowest one in under this classification. That is phosphorescence. What is phosphorescence? It is also a radiative process, and radiative process which occurs between the states of different multiplicity. That is, suppose if there is a radiative transition that is occurring between say triplet to a singlet, okay, or maybe singlet to triplet, okay, maybe some singlet to another triplet. That is, there is a change in spin multiplicity while the transition is taking place along with emission of radiation h nu. So, this is called phosphorescence, and it is a very slow process. That is, time, if you think of the time required for the process to be completed, it takes maybe even seconds. It starts from millisecond, okay, less than millisecond to maybe up to seconds. Okay, in certain cases when you use rigid matrix, solid matrix, or maybe if you go to a very low temperature, maybe 77 Kelvin, that is liquid nitrogen temperature, you can see, you can observe phosphorescence, okay, maybe visible phosphorescence, or maybe near infrared phosphorescence. Okay, so this is a very slow process. Okay, then comes the radical reactions. Now, radical reaction that occurs in the time scale of 10 to the power minus 3 to 10 to the power minus 5 seconds. Okay, it is more than microsecond, it takes time. Okay, when I talked about this radical pair recombination, that is spin chemistry, in that case in time scale of observation of the process mostly comes in the range of microsecond, okay, or sometimes it is a little faster, maybe several nanoseconds as well. So, radical reactions, it spans from -5 to -3. Okay. So, this is also a slow process, although if you think of observation by eyes, no, it is not possible, but because it is 10 to the power -5 to -3. Only thing is that you can observe phosphorescence if its lifetime is of the order of seconds, otherwise it is not possible because of the limitation of our eyes, because of the persistence of vision. Okay. Next, if you think of, there is a huge range that starts from maybe more than a millisecond down to a nanosecond, which is encompassed by radioactive decay. Okay, a huge range, -9 to -3, even more. Okay. Next, there is in violet color, you see, it is protein folding and conformational changes, okay, with time. It is again a rate process. Okay. Protein folding means biomolecules, they are biopolymers, okay, having a specific sequence of amino acid residues. Okay. And when these amino acid, this biopolymer is present in solution phase, so it is folded in a definitive pattern. It has got a folded three-dimensional structure. Okay. So, what happens is that if you change the pH of the solution, maybe you add some additive from outside, maybe urea or guanidinium chloride, or maybe surfactant, then this folded structure gets unfolded, or maybe even if you increase the temperature, then this unfolding may take place. So, this folding unfolding, it takes time. So, this protein folding and also the corresponding conformational changes, that falls in the time scale of the order of nanosecond, a little more than a nanosecond to several hundreds of microsecond. Okay. So, this time scale is encompassed by this protein folding and conformational changes, okay, that is time required to undergo conformational modifications. Okay. Say because of binding of a a second substance with the protein. Okay, what is happening that this protein may get folded or maybe may get unfolded. Okay, next look at this intersystem crossing and internal conversion. It is also encompassing a huge range, maybe -11 to a little more than -8 or maybe a little less than -7. So, -11 in between -11 and -7. So, intersystem crossing is basically, if you think of the Jablonski diagram, which is well known in photochemistry, Jablonski diagram. Which represents, which is a composite form where all the processes, probable processes, can be integrated in a single photograph or a single description. So this is your S0, S1, then maybe this is T1 or maybe higher states, say S2. Okay, maybe there is another T, this is a T prime, this is T. Okay, so this is absorption, this is another absorption. Okay, this is internal conversion, that is from S2 to S1 without change in the multiplicity, or maybe from here to here, non-radiative de-excitation from say singlet to triplet, there is a change in multiplicity. Okay, so this is called the intersystem crossing. So this is intersystem crossing and internal conversion. These are all non-radiative, that is de-excitation to another state, giving rise to heat, not giving rise to photons. So it is called the non-radiative de-excitation. So non-radiative de-excitation of these two kinds. Okay, so that has got time scale of observation of the order of 10 to the power -11 to 10 to the power -7 in between that. Okay. Again, if you think of proton transfer process, it is in the range of -10 to -9. Okay, in the range of -10 to -9. So proton transfer process. So 10 to the power -10 to 10 to the power -9. Okay, so it is also fast, and maybe if you recall the diffusion control limit parallel to that maybe. Okay, so it's reverse of this time is time constant. So time constant is of the order of diffusion control, maybe a little different, but in that range. Okay, so proton transfer falls in that range. Then abstraction and elimination reaction. These abstraction elimination reactions are quite fast. It is -12 to -10 in this range. Okay, -12 to -10 in between this. So maybe hydrogen abstraction process or maybe elimination, E1 or E2, like elimination reaction, or maybe elimination of some group. Maybe you have read in organic chemistry. So that is also very fast, in the range of picosecond to maybe sub nanosecond. Okay. Then there is another thing which is rotational motion. Rotational motion means, if you think of a molecule, this molecule can have various motions, and quantized motion, if you think of quantized motion, then it has got electronic motion, then vibrational motion, and then rotational motion. Okay. Translational motion is spectroscopically trivial because it does not represent any quantized motion. Okay. So these are the three degrees of freedom, that is electronic, vibrational and rotational degrees of freedom are there. So rotation is basically like this, maybe about the internuclear axis, or maybe like this, or maybe like this, depending on whether the molecule is a linear or is a non-linear one. Okay, so this rotational motion, it is quite fast. It is in the range of 10 to the power minus 12 to 10 to the power minus 10, a little less or more. Okay, so this rotational motion, it takes time compared to other motions like still faster motion, that is the vibrational motion. So vibrational motion is like this. Suppose you have got water, so it is like this, it is doing like this motion. Okay, or maybe like so this is a triatomic system, so or maybe a diatomic system, like a diatomic system, it is doing like this. Okay, so it is a vibration. Okay, so vibration is faster. You see, for rotation to occur, you know, this molecule, I mean atoms, this atom or that atom has to change its position. While doing that, because it does not require rotation means this atom may be transferred to here, I mean by this motion. So that means there is a huge change of position from here to here, but for vibration it is not that much. Therefore vibration takes less time compared to rotation. So vibrational motion, it is of the order of little more than 10 to the power 14 to 10 to the power minus 12 in picosecond range. Vibrational relaxation is in between vibration and rotation. Okay, vibrational relaxation means, why vibrational relaxation? It loses its energy and molecule when it gets excited to a high vibrational level, then it does like this. So energy is dissipated and thereby it goes to the lower energy level. So that is called the vibrational relaxation. So system is relaxed to a lower state. So vibrational relaxation takes in between vibrational motion and rotational motion. There is another reaction which is called the Diels-Alder reaction. Okay, so Diels-Alder reaction, it is another kind of reaction maintaining the orbital symmetry. This reaction is also like say the typical example is a die-in and die-no-fill. So you have got a die-in and a die-no-fill. Okay, so this will give rise to so typical mechanism as if this is, but it is not like maybe it is better represented by a 6-member transition state. Okay, so it's a Diels-Alder, it's a typical Diels-Alder reaction. So Diels-Alder is in between, is close to vibration relaxation, time wise. Okay, and it is also falling in between vibrational and rotational. It is of the order of 10 to the minus 13 to maybe 10 to the power little less than 10 to the power 11 minus 11. Collisions in liquid, it is average number is 10 to the power minus 14 second. Dissociation reaction is even faster compared to your abstraction and elimination reaction. It is in the range of course in the 10 to the minus 14 to minus 13. Now electron motion, it is around 10 to the power minus 15 in femtosecond time scale. This is picosecond, this is nanosecond, this is microsecond, this is millisecond. Okay, so femtosecond, and where electron motion in atoms and molecules, and also tunneling. So as I told you that if you think of a molecule, then it can have electronic motion, it can have rotational motion, it can have vibrational motion. So these three motions, electronic motion is fastest compared to vibrational and rotational motion. So I guess I just given you a rough estimate of the of the time scales of observation of various processes, and that is journey from say millisecond to femtosecond. That is means how you can reach, I mean not in terms of means in between what you encounter in between, like between phosphorescence and electron motion, what are the other possible motions that fall in between this, that is in the intermediate time scale between -15 to -3. So, there are quite a number of processes that one may be thinking of. So, when it is the question of, so here what we are going to focus on is the electronic motion, maybe vibrational motion as well, or various faster motion. So, primarily the this ultrafast region maybe somewhere over here. Okay. So, maybe -12, around -12 to -15, it is the ultrafast region. It is a very fast process. Okay. And therefore, if this is a very fast process, then you need to, of course, to observe these faster events, you need to have a very fast detecting system, I mean detector, or maybe a system which is capable of detecting this faster changing, I mean fastest changing processes. Okay. So, that is also a big challenge for this ultrafast processes. So, here to probe these ultrafast processes, we have to take the help of this light, of course light, because its speed is huge, and maybe in 1 nanosecond it travels about 1 foot. Okay. So, by so in that case you can generate the time lag between 2 successive photons or maybe 2 pulses by changing the optical path. There is a path which is travelled by the light beam between maybe one mirror and that another mirror. Okay, so that is the optical path in between that. So, from this mirror reflected to this mirror, and then it is reflected. So, this is the optical path between these 2 points. Okay, so we have to take the help of lasers. Now, it is in that case this faster process here, there is a predominance of nonlinear effects. Okay, and ultra fast pulses have their applications relevant to chemistry. Okay. Now, when it is duration is very short, so if you think of this energy time uncertainty, okay, del E del T is of the order of h cross, then if this time uncertainty is small, that is if it is femtosecond, then energy uncertainty is more. So, that means short duration of the pulses, and it has got a larger bandwidth, that is energy uncertainty is more. Okay. And high instantaneous power which is delivered to the system can cause unique physical and some cases chemical processes as well, because peak power is high. Okay. For ordinary lights, or maybe say xenon lamp is generally used for doing many spectroscopic experiment, although this is intense, but ordinary light or maybe these lights, they are not that intense because it is not a directed beam. So, it is this way divergent. Okay. So, that is why intensity wise it is small, but with the advent of lasers, okay, now traditional light sources are replaced with laser light. Okay. And laser light means intensity, that is peak power is high. If it is a pulsed laser, or even if it is a continuous laser, since the light beam is, I mean all the photons are directed, okay, therefore intensity is high. Okay. Now, A nonlinear medium is one in which the dielectric polarization vector P responds nonlinearly to applied electric field. In this case from light, unlike the ordinary case, that is P is basically polarization vector, dielectric polarization is directly proportional to E. Okay. With E0, epsilon 0 is the free space permittivity, chi is the susceptibility of the medium, and for intensity, when intensity is high, then it can be expanded to higher power. So, therefore, polarization, dielectric polarization is very much dependent on the intensity of the electric field. So, if the intensity of the electric field is low, then these terms are not that important. But when at the moment it is increasing, means suppose in case of high power laser, that is short pulse lasers, right, when it is pulse, say if the duration of pulse is very small, say several hundreds of femtosecond maybe, or maybe picosecond. So, pulse height is high and peak intensity is high, therefore, electric field intensity increases, therefore, E square and E cube terms, these are progressively increasing. So, these terms are contributing. So, therefore, nonlinear, I mean this dielectric polarization vector has got some nonlinear contribution. So, nonlinear effects come into action. Okay. So, that is why we take the help of the moment we take the help of ultrafast pulses, then the nonlinear effects are quite obvious. Okay. Now, ultrafast laser spectroscopy, basic laser principles I already have explained. Okay, I already have explained to you in another instance, that is when I talked about this laser flash photolysis. Okay, that is a modification of the conventional flash photolysis. Okay, that is a modification of the convention, and there we have talked about, I mean, ruby laser, helium neon laser, and there are many other kind of lasers. So this and there are many variations of this, like when it is a pulse laser, you may shape the pulse, or maybe you can lengthen the pulse, you can shorten the pulse. So that part is not we are not going to discuss on that, because that involves a separate topic, that is spectroscopy. Okay, so which is beyond the scope of this current course. So we will just skip these portions, but we'll just consider that here laser source is needed, and maybe depending on our requirement we need a short pulse, we need a long pulse. Okay. And ultrafast experiment, among ultrafast experiment, transient absorption spectroscopy is one of the important experiments. Okay, like flash photolysis, that is also transient absorption, but in that case your laser pulse width is longer, maybe several nanoseconds, maybe 5 nanoseconds or 6 nanoseconds or 7 nanoseconds, like that. So, of the order of 10 close to 10 nanoseconds. So, in 10 nanoseconds, that means its time window is quite long. So, therefore, if any process is occurring like even less than 1 nanosecond, then we cannot detect. That is ordinary conventional laser flash photolysis, you cannot detect much faster process, that is you cannot go down to like less than 1 nanosecond, because your laser pulse is wider. So, that is the difficulty. That is why another variation of transient absorption spectroscopy, where you use ultra short lasers, okay, is needed. Okay. So, that is called your, and another name of this is called the, and it has got another name which is called the pump probe spectroscopy. That is, you pump a system to higher level, and then in the excited state what is going on you can probe with the help of a second weak light source. Okay. That is basically what you do is you try to find out, you probe the absorption due to excitation. Is there any change in absorbance due to excitation? That we want to probe, and that we probe as a function of time. Okay. Now, there are many types of lasers. Okay. I mean, I talked about solid state, like solid state lasers having lasing material distributed in a solid matrix such as ruby, neodymium laser, that is neodymium, yttrium, aluminium, garnet. Okay. And flash lamps are in most of the cases the pump source. Okay. And this ND-YAG laser emits in the infrared region 1064 nanometer. Okay. Not 1 point, it is a typo. So, 1064 nanometer. Semiconductor laser, sometimes called the diode lasers. Okay. These are PN junctions or PN junction, these are having PN junction, and current is the pump source, and maybe it has got the application in laser printer, CD players. Okay. These are the basic application. These are semiconductor laser. Dye laser. Okay. So, complex organic dyes are used, okay, such as rhodamin B, rhodamin 6G, many coumarin dyes are used. Okay. And it is the lasing media, and what you do, and it is a tunable over a broad range of wavelengths, and depending on its fluorescence spectra, and this lasing is achieved by another laser source, that is your pump laser. Okay. Maybe that laser excites pumps your dye to the excited state, and then other processes are occurring. Okay. So, in that case, dye lasers are also tunable. Gas lasers like helium neon laser, argon ion laser, which is visible, which has got visible and UV. Carbon dioxide laser, it is in the infrared region. Okay. And are used for cutting hard materials. So, these are uses. Excimer laser. Okay. So, it is excited state dimer laser. Use reactive gases such as chlorine, fluorine, etc., mixed with inert gas such as argon, krypton, xenon. Okay. Xenon fluoride is a typical excimer laser. When electrically stimulated, a pseudo molecule dimer is produced, and excimers lays in the UV region. So, there are many different kinds of laser, and nowadays the semiconductor laser, these are also used for for pumping your ultra short lasers. Okay. So, solid state lasers are very useful, and they are having quite a long lifetime. I mean, they can run for they can be used for many years. Okay. Okay, these are the types of lasers. Now, what is the resolution? As I told you, that resolution is delta t, delta nu, that is frequency uncertainty and time uncertainty. Okay. So, frequency uncertainty is less means time uncertainty is more, and vice versa. So, for a it is irradiance versus time plot, and this is the spectrum. This one is the spectrum, and this is the irradiance. So, for long pulse, that is the pulse stays for longer time, that is full width half maxima, that is width at half maxima. So, this is your maxima. So, I am half maxima, this full width half maxima, FW HM is more compared to this one, and you see its spectrum is very narrow, whereas for the short pulse FWHM full width at half maxima, this is smaller, but it is dispersed more, its frequency uncertainty is more. So, FWHM frequency FWHM is more compared to this one. So, this comes from the uncertainty principle. So, depending on whether we want a long pulse, or we want a short pulse, or we want a spectrum which is a narrower one or a broader one. Okay. That is decided by your requirement, whether you want to probe a very fast process or a very slow process, or a slower process. So, for a faster process, you should have this choice than this one. So, this is a typical nanosecond laser flash photoresist thing, and say this is a picosecond pump probe experiment. Okay. So, how to generate these pulses? There are many ways to generate these pulses. Q switching, again I am telling you it is not, I will just name because of the scope. Okay. So, Q switching is one method. Okay. I told you, probably you remember that laser cavity requires two parallel mirrors. So, if you rotate one mirror like this way, then the moment it is exactly parallel to that, then standing wave pattern, I mean the cavity is filled with radiation, and then it will less. Again it is, if it is rotating, no radiation, again parallel radiation. So, it is some kind of switching the cavity on and off. So, Q switching is another way of generating the pulses. Okay. Mode locking is another, it can be passive or active mode locking. Pulse shortening can be done by GVD, group velocity dispersion, and pulse lengthening can be done by chirping, pulse chirping. Okay, so these are the various ways to generate pulses. Okay, what is a palm probe technique? Now palm probe technique, apart from your this laser flash photolysis, since it does in nanosecond time region. So to generate your time axis, this you just use the time axis of your cathode ray oscilloscope. Okay, you just pump your sample with radiation, and the moment the pump falls on your sample, a second detector which detects the first incoming photon onto your sample, that is a photodiode. So, that triggers your cathode ray oscilloscope or oscilloscope, and then it keeps on collecting the signal for some period. So, that generates your time axis, but here since it is much faster, so that is for your cathode ray oscilloscope. So, electronically you generate the time axis, that is you measure the time, you start measuring the time from the moment the light falls onto your sample. Okay. But if it is still faster, if it is faster than nanosecond, then electronics cannot do. It has got some basic limitation. So, therefore, you have to have the help of, you have to take the help of light to generate your time axis. Okay. So you see that this is your excitation pulse. Okay, it is divided into two. Okay, maybe it is a 50% beam splitter. Okay, then this is directed this way. Okay, so this is your excitation pulse, and another portion maybe less than 50%, that is maybe most of the pulse, maybe say 90%, not 50%, 90% is directed this way, only 10% is directed this way. Okay. So, the optical path length is from here. So, this length plus that length, then this length, and then this one up to sample this length. So, total length and this length. When these two match, then we say that these two pulses are in 0 time, that is they are exactly matched. Okay. So, that is your matching, and then what you do that you keep on changing this length by changing the position of this retro reflector, I mean this reflector, there is a pair of reflector. So, if you increase the length, then probe pulse will reach the sample at some later time. So, what you do? You start your experiment when this pump and probe, excitation pulse and probe pulse, they are exactly matched temporally in time. So, that is your 0 time. Okay, that is your 0 time. So, when they are temporally matched. So, this is your probe pulse and say this is your pump pulse, they are exactly matched in time. Okay. So, this pump pulse initiates some reaction, maybe some physical process, maybe some chemical process. Okay. So, it initiates some reaction, and then what you do, the moment it initiates, that time this pulse is present. I mean this the probe pulse. So, you collect the signal, that is how this probe pulse means how much of this probe pulse is transmitted through the sample and to the detector. So, that is basically you are measuring the transmittance. Okay. So, maybe so initial intensity, you measure the intensity of the probe pulse as a function of this delay. So, therefore, say intensity is this much, maybe you change the delay and you increase the delay, so that this probe pulse is reaching at some later point. So, that means not exactly at the very very presence of your, I mean the moment this your pump pulse is present or entering to the sample. So, after this pump pulse is entering, so your situation is here, then say your system is decaying like this. Okay. That means your active species which is absorbing, maybe because it is a pump probe absorption technique. So, your active species is maximum maybe at this time. So, therefore, let us say your signal is here. So, if your probe pulse reaches somewhere over here, then active species is somewhat less, therefore, your amount of absorption will be less, that is amount of transmitted light will be more. So, absorption will be less. In the same way, so you keep on recording your detector number, I mean how much the detector is detecting, your detector signal. Okay. So, what you do, you send your excitation pulse and probe pulse at the same time. So, that is your 0 time, and then you keep on keep on changing this delay, increase the delay, so that this probe pulse is reaching at some later point. Okay. And here this lens is used because they have to be directed at one point, that is maybe here, they should be spatially and temporally matched. They may be temporally matched, but if they are not spatially matched means suppose this volume of solution has got the excitation, I mean say because of your pump pulse, this much of solution out of say this huge volume of your solution is excited. So, therefore, you have to make sure that your probe pulse should and must pass through this region where your active species is generated. That is why this pump and your probe pulse, they are to be temporally and spatially overlapped. Temporally means their pulse should be matched at 0 time, that is called your temporal. Time wise they are matched, and also spatially they should be matched. And here is the detector which detects the signal as a function of this delay. So, if there is any true absorption, then I mean if there is a true absorption, then there will be change in intensity of the probe beam. Okay. Intensity of the probe pulse will be changed if there is any absorption, or maybe if there is any re-emission, stimulated emission, then also probe pulse energy will be altered. So, this alteration is plotted as a function of this delay. Now, this delay means how much of length this delay has been made, I mean how much of length this delay has been travelled by. So, I mean initially that said your delay is here, I mean this retroreflector, later on suppose it is shifted to here. So, this much of additional distance has been travelled distance is travelled by the light. So, that this additional length corresponds to some delay. Okay. Why some delay? Because this probe will reach at some later time, because time, I mean the light source takes time, light pulse takes time to reach one point to another, although it is very fast, but maybe if you think in this way that 1 nanosecond corresponds to 1 foot. So, that means 1 nanosecond 10 to the power minus 9 second corresponds to 1 foot, that is 30.5 centimeter. Okay. So, that means this much of this plus that much of extra length corresponds to how much of time delay. So, this way you plot, I mean you generate your x axis, okay, and you generate the kinetics of the process. and then you fit with appropriate function, so that you can generate the various number, that is the time required for a process to take place, that is the process which we are trying to probe. The thing is that the sample has to absorb your excitation pulse, and maybe it will generate some species, and that species will be probed by your probe pulse. Sometimes it is a white light, or sometimes it is close to some single color. Because if it is a picosecond, or maybe if it is a femtosecond pulse, then this wavelength separation, that is, it is a broadband pulse, it can be regarded as a broadband pulse, like this, it is a broadband pulse. So broadband pulse means you can scan for a range of frequencies. Okay, so it is a pump probe technique by which you can also follow the kinetics of the decay, or maybe kinetics of the generation of some species. Maybe suppose because of this incidence of this excitation pulse, a new species is generated, suppose because of some reaction. So that means because of the generation of this new species, maybe there is a change in probe pulse energy, so that you have to monitor. Okay. So as I told you, white light may be useful for this. So for generating the white light, maybe quartz, or maybe ethylene glycol, okay, or maybe a sapphire plate is useful. And if you shine this sapphire plate, or maybe quartz plate, or water, pure water, and if you shine, if you focus this ultra short laser onto this water, then white light will be generated, and with the help of a dispersing medium you can generate all the frequencies. Okay. So it is ranging from mid UV to mid IR region. So therefore, using ultra short light sources, you can generate a white probe light, okay, which is essential for following the doing the absorbance spectroscopy of the excited species. Okay. So this palm probe is a transient absorption experiment. Transient absorption experiment means you generate the species, it is transient species, and with the help of another second probe, second probe means another probe, you look into the concentration of that species, and that species is not present under ordinary circumstance. Only because of your laser incidence, when laser falls on that, because of your laser incidence, this transient species is generated. So transient absorption gives you a lot of information about the processes that are going on, that may proceed immediately after laser excitation. That laser may be your femtosecond laser, maybe picosecond laser. So it's basically a pump probe technique, like your laser flash photolysis. Only difference is that here, to generate your time axis, you have to use the delay, okay, because otherwise if it is a picosecond process, then by the help of electronics you cannot generate the time axis. That is, you shine with light, and if you want to follow this change of intensity with time by means of a photodetector and your oscilloscope, it is not possible because of the time limitation of the electronics. So for nanosecond flash photolysis or even microsecond, oscilloscope is useful because there is no problem with its limitation and also the time scale, but here it is the problem. Okay, that is why we have to use here this device. Device means for generating your time axis, that is, we are taking the help that the pulse requires a time from here to here, that is a time difference, that may be very small, but that we will be using to generate your time axis. There is another technique which is called fluorescence up conversion technique, that is amalgamation of 2 photons, okay, amalgamation of 2 photons to generate 1 photon. Okay. So, that we will take up maybe in the next piece of lectures, in one of the next pieces of lectures. Okay. And so what we have learned from this discussion. So, remaining part, that is other different experimental things we will take up one after another, but up till now what we have learned, let us try to go back, that we have talked about this various time scales of observation of various processes. Maybe it is from your millisecond to femtosecond, and these processes are very important in chemical sense, in chemistry. Okay. Maybe sometime in chemical biology as well, like we see our vision. Okay. That is also a light driven process, sometimes light driven activity of some antifungal or some agent, maybe photodynamic therapy, there also light is very important. Okay. So, we talked about this, tried to understand the various time scales, then we gave a brief introduction of nonlinear effect. To see this nonlinear effect, we need ultra fast lasers, and then types of lasers we just talked about a little bit. Then resolution is an important factor. We are when it is resolution, we are compromising, and time resolution, then we are compromising onto frequency and vice versa. Now, various pulse shapes can be, whether it is long pulse or short pulse, that can be generated, and depending on our need, depending on the time scale of observation, we can generate short pulse or long pulse. And we discussed out of various ultrafast techniques, pump probe is one of the popular techniques. Okay. So, and white light is also useful for that, and how this is done, that also we just try to give you the idea. So ultrafast processes are very interesting and very important in many cases. So, we will take up one after another, and actually this using this ultrafast spectroscopy, people scientists have been able to probe the transition state. Okay. So, observation of quantum bits, and that we are going to take up maybe in next pieces of lectures. So, in the next lecture we will talk about other examples, different experiments. Okay. So, that we will take up. So, till then, thank you.